Hello, this is Patrick O'Shaughnessy. This is the 7th module in the series Statistical Methods for Analyzing Data Obtained in the Lab or Field. As you can see here, we're going to be discussing continuous random variables, and it's focusing in on what's known as the normal distribution. Now let's just start right away. And what is a continuous random variable? From your measurements that you are taking in the lab or field, the presumption is that you are collecting values that are on a continuous time frame, length frame, whatever. These values can be minimized only all the way down to whatever the resolution of your instrument, right? They are not discretized, so they are not integer values of 1, 2, 3, 4, etc. Those would be referred to perhaps as discrete random variables. So we're going to focus in on continuous because that is typically the type of data you would be collecting. Here's the module map. We are in the grouping of modules called statistical tests, as you can see here, and we're working our way towards an understanding of the statistical tests. So these 6, 7, 9, and 10 should be taken in a series. 8 is kind of a peripheral in terms of the log normal distribution. So let's get started. First concept is this thing called the probability density function. So if you have measurements that are continuous, you just keep splitting it down, right? They're not discrete, they're not integers, they are random variables such as concentration or height as examples. So you could determine a range of the variable with a histogram, as we saw in the first module. And as you can see an example of that down below, where we have data that's scattered between about 6 and 14 with some sort of a mode around 10.5. And if you narrow the histogram bins to near 0, as shown here, you could keep dissecting so much these bin widths to get more and more fine-tuned idea of what the distribution looks like. You would ultimately get to a smooth curve, or at least a smooth curve that best estimates the distribution that these measurements come from, the apparent population distribution, you could call it. So this is a probability density function. It gives basically the frequency of events relative to the actual values on the x-axis. Okay, so this distribution, as you can see, was characterized by the bell-shaped curve. Most of your measurements are in an area close to the average, and then there are less and less of them as you get further away from the average. That's what formulates the bell-shaped curve ultimately. So it's characterized by 2 parameters, the mean, central tendency, and the standard deviation or spread or variation of the curve. And as you see here, there is the equation for this probability density function of the normal distribution. You can see sigma in there and mu as well, that characterize again the central tendency and the spread. This particular function can be used for any set of mu and sigma to come up with the associated bell-shaped curves. So here's an example of it again, but there are an infinite number of such normal distributions, obviously, because of an infinite number of possible combinations of mu and sigma. So the next most important aspect of analyzing a distribution is we would often like to know the area under the curve. We would want to know, because it would allow us to understand the probability of occurrence of values within the population. And hopefully that'll become more obvious as we go along here. Now, in order to get the area under the curve, we would have to integrate the PDF. Right? And with an equation for the integral, we could easily put in some values, say, that for which we want to know the area under the curve up to that value, for example, everything less than it. However, as you can see here, for that particular equation I just showed, the normal distribution equation, the cumulative distribution function, this integral, cannot be determined mathematically. No one's been able to figure out how to integrate that equation. So the best that has been proposed are some approximations of that curve. However, back in the day, someone came up with a brilliant idea of coming up with one curve, a standard PDF with a standard CDF that could be then put into tables. And as you'll know, most statistical test books have tables in the back. Those tables are to give you the approximate value of the cumulative distribution function, because it cannot be just cranked out through an equation. So the standard PDF, they had to choose then, well, what would be its central tendency and standard deviation? And it became obvious, let's make it have a mean of 0 and a standard deviation of 1, and they called it Z. So there is a mathematical transformation that occurs then between the values that you have and their conversion into Z, and it's rather simple. You just subtract the value you have from the mean and divide by the standard deviation. Subtracting it from the mean will put Z above and below the mean line, right, which would be 0. It would be, the differences would fluctuate around 0. And then dividing by whatever sigma is will normalize it to the actual sigma and cause it to have a sigma of 1. So Z is a special value, a special table of or variable that has a mean of 0 and a sigma of 1. With the use of Z, then, they could come up with these approximations for the area under the curve for just one of the infinite number of possible normal distributions. So here is a closer look at the relationship between the PDF and the CDF. So we've seen the PDF that's generated by the equation, and you can see this PDF of Z, as we would expect, is centered at 0, and here are the values of 1, 2, and 3Z, but we know that those are also, Z is essentially the standard deviation. So a Z of 1 is truly one standard deviation from the mean. So this line here is representing the area under the curve between the mean and one standard deviation away. Now if we look at the CDF, again, that gives us the area under the curve directly. We could go to 0, come up to the curve, look over, and see 0.5, which is exactly what we would expect, that 50% of the distribution is less than the mean. That's this entire area right here. The Z of 1 is again equivalent to a 1 standard deviation from the mean, and if we move up the curve to there, we come across it's somewhere between 0.8 and 0.9. To be more specific, it's around 84%. Okay, to split this out even further is another graphic here to just help you visualize these areas, because it's going to be very important down the road. When we talk about having 95% confidence that something's different from something else, it's all going to be associated with this as the area, so to speak, from which that confidence is mathematically derived. So that's the importance of this. So across the top is the area under the curve from minus infinity, which is how far out this curve goes. You can see it by -4, which is -4 standard deviations, or 4 standard deviations from the mean. There is almost nothing out there. It is extremely unlikely to actually get a value less than 4 standard deviations from the mean. As you can see down here, your probability in a sense here is practically 0 at that point. And to give you an idea of what that's all about, we can start at minus infinity, come across, and we see these various probabilities, We're up to 2.3 or so by the time we get up to 2 standard deviations, around 16 at 1, and of course we're at 50 by the time we get to 0. There's that 84. So that means 84% of all the values in your distribution are less than 1 standard deviation. That's this entire area of the curve up to 1. That's what these numbers across the top mean. The numbers down here are those between, within, in a sense, within the distribution. 34% are between 0, the mean, and 1 standard deviation. 68% therefore are within plus or minus 1 standard deviation. So this helps also to understand the idea of standard deviation. All standard deviations then are plus or minus around the mean, occupy about 68% of the distribution. That is true for all of them. Now you get out to plus or minus 2 standard deviations, you can see you're almost at 95%, actually a little over 95%, 95.46. And then by plus or minus 3, encapsulated almost the entire distribution, 99.73%. Okay, so for example, we have a distribution with a mean of 5 and a standard deviation of 2. For whatever reason, we want to know the probability of finding a value less than 8. Now, hopefully graphically in your mind, you can kind of envision this. 8 is to the right of the mean on the distribution. So I expect something over 50%, right? So this is essentially, what percentage of values in the distribution are less than 8? Well, the classic approach to this is to first convert this 8 into its equivalent z value. Again, we just apply that simple formula. So 8 minus 5, the mean, divided by 2, we get 1.5. So a value of 8 is 1.5 standard deviations to the right of the mean. That's one way to think about it. But we want the probability, which is, again, integrating that PDF from minus infinity, I should say minus down there, to 1.5. Can't do it. So we have to go to an approximation function or go to a table, a z table, to get at that. So thankfully Excel has such an approximation function. It's called norm.s.dist. You plunk in the value of 1.5. It already knows that the mean is 0 and the standard deviation of z is 1, so you don't have to put that in. But that little extra 1 on the side right here means give me the cumulative distribution, the CDF value. If it's a 0, it'll give you the PDF value, which is really not useful to you at all. So always put a 1 in here. Then we see 0.933, or 93% of all values are less than 8. So that's the answer to the question. Now there is one other way to do this in Excel, which is to use just the norm.dist function, in which you manually put in all of the values necessary to understand the area under the curve that you're interested in. So the first one, 8, obviously is the number you're interested in. Then you have to supply the mean, then the standard deviation, and then this 1, which stands for give me the cumulative distribution. You'll get the same number again. Again, with the S in it, it already knows that the mean is 0 and the standard deviation is 1. So this is how we can apply Excel, again, to get at these probabilities. So here, just pictorially, is what's going on. Again, we are at z of 1.5, so we are interested in the area to the left of 1.5, which is everything here in purple. Again, going down, knowing the CDF, the values, thanks to the approximation functions, we come across here and would end up with somewhere between 0.9 and 1 if we were using just this graphical method, and we know it's 0.93 specifically. So that's what we ended up with, was 93.3% of the area under the curve for a value of 8 when the mean happens to be 5 and standard deviation happens to be 2, which gives us a z of 1.5. Let's see how they're all kind of related here. Now the other part of this that we want to introduce now is what's called the tail area. We're going to see that it's actually the tail area that becomes more important to us when we get into the concept of a t-test or determining confidence. So the tail area here is simply just the inverse of whatever we have. It's the remaining area under the curve, correct? So it's 100 minus 93.3, which is 6.7% here. Okay, as it says here, all parametric statistical techniques are valid under the assumption that the data is normally distributed. These parametric statistical techniques, as we'll talk about in a bit, are a t-test, a z-test, and ANOVA. They all have as their basis that the data is at least mound-shaped, somewhat normally distributed. They're fairly robust, as they say, to being somewhat off normal, but we'd like to know, is the data normal enough? So one way to get at that is to plot it and what's called a normal probability plot, which is a graphical method, and it's kind of easy to understand, so we will go through that now. Okay, just to go back to the module 1 information, recall that an exponential function, you could say, is kind of straightened. It's made linear graphically by applying the function to a log scale, as shown here. So this is the semi-log graph paper. The same can be done with the CDF curve, which is kind of what they call a sigmoidal curve. It has kind of an S shape to it, and it can also be straightened with what's called a probability scale. So you see here that the scaling can go from 0.01 or even smaller, so it's a small fraction, up to 0.99. The values around 50, you can see, are fairly evenly spaced. That's because the sigmoidal curve is rather linear, so you can expect to have even spacing. But as we're trying to straighten this curve as it goes more and more asymptotic, as it's called, the plot graphing, the paper itself also shifts to wider and wider margins, both above and below the 50% line. So that's what a probability scale is. And again, has the same purposes of being able to easily pick off information, as we'll see. Okay, so how do we construct this normal probability plot of our data? First thing you have to do is rank the data, low to high. If you're doing this in a spreadsheet, best to just copy the values over to a new column, preserve your old ones, and rank them low to high. Then you're going to put another column next to that, which is just the ranking values, 1, 2, 3, 4, 5. Then you'll have a third column that computes the probability based on the ranks, the 1, 2, 3, 4, 5s, under the assumption that the lowest value that you have obtained would have a low probability, and your highest value would have a high probability of being, at the end of the distribution. So that's how this kind of works intuitively. So it's a simple little equation here. The probability that is expected to be at this data value, it will have the ith rank, say 1, minus 0.5 divided by your number of total data values you have, n. So for an example, you have an n of 100 observations. Then let's just take a look at how it calculates out the 50th rank value. So you put in 50, minus 0.5 divided by 100 gets you to 0.495. 51, as you can see, gets you to 0.505. So it bounds 0.5000, which again is what we expect from what we know about the median, right? The median for even valued numbers is the average between the one just below the 0.5 value and the one just above it. So it applies these probabilities directly to these rank values. And then you plot these probabilities relative to the corresponding values, the ranked values, I should say, on normal probability paper. Okay, so there's one little glitch in all this. A probability scale is not something you can just ask Excel to give you as one of the options in its graphing platform. So why not? We don't know, but that's the reality. So we can't reproduce that probability scale I just showed you 2 slides ago. That was done in a different software package. However, we do know there's a relationship between probability and the associated z-value, and the z-value is linear, and we can easily plot linear values. So for example, we could go through the equation, but we know that the z-value of 0 is the mean, right? And it is on the 50% line. 50% of the distribution is below it, 50% above it. So that's the conversion, the transformation of a probability of 50% would be a z-value of 0. Likewise, a probability of 84.3% we know delineates exactly where the z-value of 1 resides. It's 1 standard deviation. So that's the mentality here in terms of the transformation of probability to z. And then we can just easily plot these z-values instead of a probability scale. So my apologies, you have to go through this one extra step to do this in Excel, but that's what needs to be done. So for example, here we have our set of data going down. As I suggested, best to just put it in a new column in case you want to preserve your raw data, and rank order it using the data rank function in Excel from low to high. Apply a column that is the rank order from 1 to 20 in this case, and then compute this p-value based on this equation up here. So in this case, it's going to be C3, which is a 1, minus 0.5 divided by this $A, $1 is locking in on this value of 20, in which case I use the count function to count up all these values. Of course, you know it's 20. You can just put it in automatically. I have to multiply by 100 as well in order to get it into a percentage value, 0 to 100 instead of its fractional form. Likewise, then, you can use the norm.s.inverse function to get the z-value. So from probability to z, we go kind of an inverse. And here we have to divide by 100 because the function takes the fractional form. So once you have, I can just add here that if you don't have the 100 up here, you don't need the 100 down there, and just work in fractional form instead. Okay, so once that's done, now we are going to be able to plot the sorted data values, column B, versus the z-values that we've computed in column E instead of the probability values, because they are not going to line up in a nice linear fashion like the z-values will. So again, we know that that 0 right there represents 50%, the 1 represents 84%. And the point here now is, are these data values lining up? The answer is yeah, for the most part they are. They're never going to be perfectly lined up. They talk about the fat pencil test, in which back in the day you print it out, put a fat pencil on it, you don't see most of the points, you go, okay, good enough. It is normally distributed. And that's the basic idea here. Is it normal enough? In which case this line will be straight enough. You may see a few excursions on the ends here because of extraneous values on either tail. Okay, there's some information you can get out of a graph like this automatically. And again, this was used back in the old days to easily get at the mean or the median of this distribution. For example, it would be the value corresponding to a z-value of 0 or a probability of 50%. So you can see that here. We have a value of 0, just come across, read down, end up somewhere around 9.5. There's your mean. Likewise, the standard deviation exists one standard deviation away from the mean. It is at 11.8 is what I read off this chart. However, remember that standard deviation is the difference between what's the value here and the value at 50. It is this distance, not the entire distance across as the 11.8 is. So don't forget that you have to subtract then the 11.8 from the 9.5 to get a standard deviation of 2.3. So we have a Z, or what's officially referred to as a probit scale. This is a normal probit graph, normal probit, instead of normal probability.